Okay. Yeah, we are recording. Let's get the slideshow set up for a current slide. And let me go over the last few announcements. We've already been talking about one, but since some of you came in since we were talking about it. Thursday is Honors and Awards Day. I think technically that's 10 till 12. So over on the Birmingham West Campus in the gymnasium, which is also called the Arthur Schwartz Fine Arts Building. 9 to 12. Okay. Yes, okay. The ceremony is 10 to 12, but the people who are in it have to be there by 9. So that means my office hours are fairly, not completely shot, but partially shot on Thursday. Normally I'm 10:45 to 1:15 when this class starts, because we'll probably be over there at least until 12. They seldom get things finished on time. Well, they seldom start things on time. But if we do end at 12, it'll take me at least a half hour to get back here to get everything done and back here. So that will be 12:30. So my office hours will be more like 12:30 to 1:15. Not very many office hours, but I will be back as soon as I can. So if you're waiting for me, hang on. I'll get here as soon as I can. But don't even start looking before about 12:30. Okay, then Friday, normally I have office hours on the Birmingham campus, 7:45 till 1. Not this Friday. I've got an infusion this Friday. It starts at 8. I have to be at the clinic by 7:45, so I won't be on campus then. And it usually goes until 4:30, and I'm not going back to campus afterwards. So I shouldn't be driving that far after that. So that's pretty much where we are with that. Okay, any questions or anything before we get going today? Now, we talked about temperature scales last time, and we actually did them in lab, so you've done most of these formulas a time or two. Now, that is one thing. Is anyone here that did not get the lab last time? Did you? Okay. Let me see if I've got it. I was short a few labs for some reason this time. I do have one more. I have to. Did you not? You don't either. I think someone got you a copy though. Yeah. Okay. All right. He's got one for you. Okay. That was what I was saying. I had promised that we would. I would answer any of the questions that you might have, because we were sort of pressed for time at the end, and I may have just given away my last copy. Here we go. I have my original. If anyone else needs a copy, I'll have to make some, because, like I said, I was short just a couple. I thought I had enough, but then I realized I didn't. So were there questions from the lab? Okay. What's that? Oh, on the questions. Okay, if you weren't here, you'll have to get with somebody and do it, or get with me sometime and make it up. So either way. If you got a copy, do you have his yet? It's called Experiment 16 Thermometer Fixed Points. Okay. All right, are there questions? Just for while you're looking, since those who've just gotten it, you'll need to read the first page. The procedure, we go fairly close to this. We had thermometers in the ice and you measured temperatures. Our heat generator was not quite as fancy as the one here, but it did its job. And specifically, you were to follow the steps pretty much 1, 2, 3, 4. And the only difference is we didn't do 2 trials. I gave you 2 thermometers. So thermometer 1 and thermometer 2 rather than trial 1 and trial 2. Okay? And then when you finish recording the data, and the way these labs are put together is sort of bizarre, you fill in the data on the data tables as you're doing it, and that was on page 152, and you filled in that stuff. Now, if you listen on YouTube, you'll follow pretty much what we did, and I couldn't always write on YouTube because we were in the lab and I didn't have a thing to set up. Maybe a little bit I did, but I think you'll be able to hear what we did. So you fill in the data table on page 152. You should have at least one answer in every blank, except your barometric pressure. You'll probably have 2 answers, one in inches of mercury and one in, what do we use? Millimeters of mercury. So you'll hear us talk about that. So you'll have 2 answers in that blank. Deviation from normal, you have deviation for your barometric pressure, also deviation in temperature. So you have 2 answers in that blank. And by the way, you only do all the stuff, I mean, you recorded everything for both thermometers. It says trials, but it's thermometers. But you only have to really do the detailed stuff for your better thermometer, the one that has the better records. So your accepted boiling point then, and then your measurement error of boiling water. So everybody okay with those, the data table? Those who are here, okay? It involved a graph, and everybody got the graph? Is that okay? Now, you also have results back at the first part, that is 149. 5 questions there you're to answer, okay? And then we also did going further. On page 151, what is the value of the slope? And this was based on the graph that you did. Value of slope, value of the y-intercept, and then number 3. So those 3 questions have answers. Actually, number 1 has 2 answers. What is the value of the slope and what's the meaning of the slope? Number 2 has 1 answer, and number 3, I think, has 2 answers as well. Write the equation for the Celsius Fahrenheit temperature graph and what's the meaning of that equation. And then we also did an invitation to inquiry. We didn't do the full part, but we did. I washed out an aluminum pop can and put a small amount of water, heated up, did all that stuff, and then explain what happens. You don't have to do it in terms of Charles' law, Boyle's law, because, but the molecular point of view, that's what you need to do. And if you were there, you should have recorded what happened and then do it. So it's an invitation to inquiry, number 1, just from a molecular point of view. Okay? Yeah. Okay. Now, for the graph, what I asked you to do was pick your better thermometer. You have 2 thermometers, freezing point and boiling point. Which one, the thermometer that had closest on both ends, the best thermometer, and then convert the boiling point to melting point to Fahrenheit and the boiling point to Fahrenheit. And that's using these formulas that we have right here. Okay? You had degrees Celsius of freezing point, convert that to degrees Fahrenheit, and you also had degrees Celsius of boiling point, convert that to degrees Fahrenheit. And that's what you plotted on the graph, okay? And did you have a specific question there? Or? Okay. What I suggested and what they told you to do Okay. On page 151, going further. Using the data from your best thermometer, not trial, but thermometer, make a graph by plotting Celsius on the horizontal axis and Fahrenheit on the vertical axis. So what I suggest you do is turn the page like this, lettering mode. You got Celsius down here. You have 1, 2, 3, 4, 5, 6, 7 blocks. So basically you do 0, 20, 40, 60, 80, 100. Okay? 0, 20, 40, 60, 80, 100. Okay? That's your Celsius scale. Now your Fahrenheit scale, you can't get quite everything on there, especially if you start at 0 here, unless you do 0, 30, 60, 90, 120, 150, 180, 210, 240. Yeah, you can get it if you do that. Okay? And I think that's probably the best way to go. Okay. And then you plot your from your better thermometer, degree Celsius, degree Fahrenheit, that's freezing point, degree Celsius, degree Fahrenheit, boiling point, and then draw your best straight line from there. Then you calculate the slope of that line like we usually do, and from there you continue with the going further. Calculate the slope of the straight line, write it here and on the graph somewhere, then answer the questions. Now, is that where you have the questions? Okay. So, any questions from anybody? I'll be glad to try to answer them. I know we were kind of rushed at the end, but we can go over it more slowly or whatever. I just wanted people who weren't there to understand where you go to the different pieces of it. Okay. Something specific? Anything?
You said degree Celsius, degree Fahrenheit. I'm saying, we calculated that.
We got try to make it already wrote down.
Yeah.
Convert that to Fahrenheit.
Right here. There you have. And which of these is better? Is it about the same? Yeah, they're identically the same in both, right? So it doesn't matter which one you do. Convert, which one you want? One or two? Right. So pick one. Two. Okay. Two. Okay. Convert that to Fahrenheit. And I would write it here. You know? And here's what you do. You put 0 in here. 5 ninths of 0 is 0 plus 32. So there's your degree Fahrenheit. 32 degrees Fahrenheit. Now, if you didn't have 0, yours isn't going to come out this way. He happened to have 0. Okay? And I think your other one was 102 or 103 or something like that. Okay? But you're not going to get any better than 103. So let's do 9/5 times 103. Do that on the calculator, add 32 to it, that'll give you degrees Celsius. Write that in. I mean degrees Fahrenheit. Write that in. And then you go to your graph and plot those. And let's just say it was 0, 32. Whatever, yeah, wherever your 32 is here, that would be this one, and then over here you have 100, and whatever that turned out to be, and you plot that, or 103 and whatever it turned out. And then you draw your line using a straight edge, and then calculate the slope, rise over run, like we've done before. Okay. Any other questions? Okay. And we'll have some time in lab today. I think the lab won't take you that long today. It's going to take me a while to set up, but if I can get a few volunteers to help me get it set up, then we can get it done a little faster. And we'll go from there. I think we'll have time to do some of this if we need to. All right. Any questions? Okay. Got it? Okay. All right, now, we're on page 92 or somewhere thereabout, depending on which edition of the book you have. There is a closer look, which I found pretty interesting. Of course, I'd read this kind of stuff before, but if you haven't, you'll probably find that a pretty interesting one. Goosebumps and shivering, what you do when your body gets cold and why you do that. It's a really interesting little blurb. I would recommend reading that. But we're moving on to heat. Basically what we did, the title of the chapter is Heat and Temperature, but we did temperature and now heat. So let's look at heat. Heat is a form of energy transfer between two objects. Now quite often, and I'll do it too, I'll say heat is thermal energy. Not quite. Heat is transfer of energy between two objects. Okay? If that hot plate is hot, by itself, it doesn't have heat until it transfers it to somewhere else. Of course, it could be transferring it to the water in the pot or to the air around it. So yeah, it is transferring heat. But heat is a form of energy transfer, not a form of energy, but a form of energy transfer between two objects. Now, we have at least two different types of energy. External energy and internal energy. Let's see what external energy. And this is energy transfer. It could be either or both. A total potential and kinetic energy of an everyday sized object. So let's say we had a hot plate there. The external energy is the total potential and kinetic energy of that object. Okay? Or let's say it was his cup of drink there. Okay? Whatever the energy is in that. The internal energy is the total kinetic energy of the molecules in that object. So that's the internal energy is the total kinetic energy of the molecules, say, in his glass of water. The external energy is the total potential and kinetic energy of an everyday size object. Internal is the kinetic energy of the molecules in the object. The external can be transferred to internal, resulting in a temperature increase. If we were to put his glass of water, or whatever he's got in there, tea or whatever, onto a hot plate, of course that's styrofoam, that wouldn't be a good idea, but if that was something that could handle that, then the external energy of the hot plate could change and would speed up the internal energy of those molecules, which would result in a temperature increase. And it could also, external could be transferred to, or internal transferred to external, resulting in a temperature decrease. That could happen as well. Okay? Now, you've seen a picture similar to this before, and I think I've done it, shoving the desk across the floor. You hear the noise when the legs make that on the floor. See if I can do it. Yeah, you can hear something going on there. Okay, hear that. Obviously, there's some friction down there. Okay? Well, I'm exerting external energy on the desk. That's moving the desk across the floor. Again, that's an external thing. But those molecules moving, and if you had a really sensitive thermocouple down there, you would have seen the temperature go up just a little bit when they went across the floor, because the molecules would be moving at a more rapid rate. Okay? The external energy here, internal energy, that little bit of heat that's released from the frictional energy. So, when you have an increase of heat, does that mean you change temperature? Not necessarily. If you have a difference in temperature, does that indicate a difference in heat? Generally, but not to a fixed type thing. And here's what I'm talking about. Okay. Temperature is a measure of the hotness or coldness of an object. Okay? And we'll get to some specific examples in just a little bit. The measure of a hotness or coldness of an object. It's based on, and we've said this several times before, the average molecular kinetic energy of those molecules. Okay? That's what temperature is. Now, what heat is based on the total internal energy of the molecules. Not an average, but the total internal energy of the molecules. Okay? Now, here's sort of a dumb example, but it really does base it. Okay? Let's say I have a bathtub here full of hot water. Okay? Or just tepid water. You know, moderately warm water. And I have a thimble full over here of really hot water. Which has more heat? The bathtub full of warm water or the little thimble full of really hot water? Okay, that has a higher temperature. There's more heat in that. If I were to place this in an ice bath, that wouldn't melt very much ice at all. That would probably melt all the ice. Okay, that has more heat than this. But because heat is the total internal energy of the molecules, there's a lot of molecules in there, so there's a lot more heat. The average kinetic energy, because the few molecules you have are moving faster than they are there, this has a higher temperature, but that has more heat. I know it's sort of picky, but that's the difference in heat and temperature. Huh? Well, that's just how the definitions are. Okay? And here's another way to look at it. If I had a quart of hot water here and a pint of hot water here, and they're at exactly the same temperature, which has more heat? Same heat? The quart has, because there's total number of molecules is a lot more. In other words, if I put the same number of cubes of ice in each of those, they would melt faster here than here because this has more heat, because it has more molecules at that increased temperature. Okay? So that's what they do it here. 1 liter of water at 90 degrees Celsius, what would that be? Yeah, it would be well over 100 Fahrenheit, probably close to 190 or so Fahrenheit. Okay, maybe not quite that much, pretty close. It's really hot, and this is 250 milliliters, a quarter of that, but at the same temperature. Okay, which has the temperature exactly the same. The heat, which has more heat, big time. 4 times more heat on general because you got 4 times more water. You need 4 times more ice to cool it to the same temperature. Okay, so it has more heat. So temperature and heat, they're related for sure, but they are not measuring the same thing. One's measuring average molecular energy of those molecules. The other is total internal energy of the molecules. Okay. So here's another definition of heat. We've already given one. A measure of the internal energy that has been absorbed or transferred from or to another object. Again, heat is dealing with the transfer of energy, not just how much energy there is. A measure of the total of the internal energy that has been absorbed and transferred to another object. Now, 2 related processes here. And they're not the only 2 processes, but 2 related processes. One of these is heating, of course, increasing the internal energy of the sun. In the lab, when we had the beaker of water sitting on the hot plate, it was increasing its internal energy. The temperature was going up. But remember, once it started boiling, did the temperature continue to go up? But I was still adding heat to it. So we'll get to that in a minute. Cooling was decreasing the internal energy. Now you did that through the thermometers, so you put them in the ice, with a little bit of water at the bottom. And it decreased the internal energy until it got down to near 0. But then even though the ice kept melting, the temperature didn't change anymore, did it? Okay, that was one of your questions. So, temperature methods or heating methods. One thing is a temperature difference. If you have a temperature difference, heat is going to be exchanged from one object to another, for sure. Okay. In fact, sometimes, a lot of times in physics, we'll call that a gradient. You have pressure gradients, you have temperature gradients, you have concentration gradients. That's usually what drives anything. Voltage gradient, voltage difference we call it, a temperature difference. Energy always moves from the higher temperature region to the low temperature region. Always. Okay? Now I can remember, I can't exactly remember this, but I can easily imagine hearing somebody, my father or somebody say, close the door, you're letting the cool out. Was that quite accurate? No, you're letting the heat in. The energy always moves from higher temperature region to lower temperature. Now, sure, you're letting the cold air blow out. Yeah, you were doing that, but really, heating is a transfer of energy, and the energy always transfers from high to low. Just like voltages, you go from high voltage to low voltage. In concentration gradients, you go from high concentration to low concentration. However, that's not the only method of heating. And this was something else we observed, and it is energy form conversion. You transfer of heat by doing work. Okay? So you're changing the form of energy so that heating, as in your internal combustion engine, when you have the explosion of the fuel inside the piston and it pushes the cylinder down, now you're using some of that energy to do work rather than raise temperature. Sure, the temperature goes up, but that's not the only thing. You actually are doing work. Now that's just another instance. We still have another one to hit. We're not quite there yet. Okay? We've talked about how to measure temperature. How in the world do we measure heat? Does anyone know the basic units? A little bit of history lesson. Remember when we talked about good old Aristotle? What was one of his 4 elements that wasn't an element?
Fire.
Fire, exactly. He called fire one of the elements. And it's not, okay? But even after the scientific revolution, after Galileo, after Newton, after Lavoisier, after many of the others, when they did a periodic table or started forming those, Lavoisier was one of the first ones, they included this element called calorie, which was heat, okay? It's not an element, but for centuries, for millennia, they thought heat was an element. It's not. But the word calorie comes from the name, the French name, which probably comes from the Latin, that is talking about energy. Okay? So the metric unit, now this is an SI unit. The metric unit, one of the early ones was calorie. And it was defined this way. The energy needed to raise the temperature of 1 gram of water. Now remember what a gram of water is? 1 cubic centimeter. That's the distance across your little fingernail, wide, high, and long. It's pretty small. Okay? 1 gram of water, 1 degree Celsius. And 1 degree Celsius is a reasonable, but not a huge change of temperature. So a little c calorie is a very small amount of heat. So since it's so small, they typically go to kilocalories, which means what? 1,000 calories. And for a long time they say kilocalories, and they mention kilocalories, they use kcals, And after a while they got tired of writing that, especially the lazy nutrition people, okay? They weren't real scientists, no. They got tired of writing kilocalories and saying kilocalories, so they changed it and went back to calling them calories, but they call them capital C calories. Now, do any of you have any, can I borrow your, does it have on it, this is Lipton, 20 calories. What kind of calories are those? Little c or capital C calories? Capital C. They're talking kilocalories there. Okay? 1,000 of these calories. Okay? That's the energy needed to raise the temperature of 1 kilogram of water 1 degree Celsius. 1 kilogram of water is going to be a lot of water. That would be probably pretty close to, this isn't water, but if that were water, pretty close to what we got in there, I think. Would be close to a kilogram of water. To raise that 1 degree Celsius, you have to have had 1,000 times the heat of what you do for 1 gram of water. Now, that's still not an SI unit. It is a metric unit, but it's not an SI unit. Now, in the English system, or the British system, in the U.S. customary system, we often measure heat in BTUs. And I think we still use this some, though more and more we're getting away from this. Air conditioning systems quite often are rated in BTUs, right? Okay. But everywhere else in the world, they don't use BTUs. I'm not even sure they use it in Britain anymore. I bet they do, but I'm not even certain of that. Well, they go mostly metric too. That's the energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Now, a pound of water is a whole lot more than 1 gram. 1 gram of water is this. 1 pound of water, you got a general idea what a pound is. Okay? This, by the way, was, this is fluid ounces. It doesn't give what the weight ounces is, but it's probably not too far off from what the fluid ounces is. Okay? That's a lot more energy than a little c calorie, but not as much as a capital C calorie or a kilocalorie, because 1 pound of water would be, well, 1 kilogram of water would be 2.2 pounds of water approximately. Okay? And 1 degree Celsius is close to, remember, twice as much as what a degree Fahrenheit. Remember that one? 9 to 5, 5 to 9. So 9 degrees Fahrenheit for every 5 degrees Celsius. So a Fahrenheit degree is smaller, but a pound is a lot bigger than a whole lot bigger than a gram, but not quite as big as a kilogram. Now, what's the mechanical equivalent? This is the SI unit for any kind of energy, including heat energy. It's the joule, not the calorie, not the big C calorie, this. But even then, a joule is a tiny, tiny amount of heat because it takes 4.184 joules to make 1 little C calorie. So that would be 4.18 kilojoules to make 1 capital C calorie or kilocalorie. Okay? Not a bad conversion to know. You don't have to memorize it, but know to look it up.
So what's it mean when it says this thing got 120 calories?
And what about it?
Okay. What's it mean when it say it?
Okay, very good question. Okay, now, and this is really surprising. Do you ever lift weights? PE or something? Huh?
Yeah.
Okay, so name one of the weights that you typically lift. Okay, yeah, but weight. How much weight?
10 pounds.
I know. Give me a typical.
25 pounds.
25 pounds. Okay? Now, 25 pounds would be about 10 kilograms. A little more, but let's just use 10 kilograms there. But think of that as 25 pounds. 10 kilograms. Okay? And how far do you usually lift it? From what to what?
I don't know what I'm doing.
Well, yeah, make up a typical.
Your feet to your head.
Huh?
Your feet to your head.
I can't hear.
Or your feet to your head.
Oh, feet to your head.
6 foot.
6 feet. Okay, that's about 2 meters, right? Okay. So you're lifting 10 kilograms, 2 meters. That's 20 kilogram meter. Multiply that by 9.8. Let's do it. just for general purpose, another 10. That's 10 kilogram meters per second squared. Like meter squared per second squared. Okay? So that would be the amount of work of, 10 kilograms times 10 meters per second squared, that's 100, times 2 meters, that'd be 200 joules of work. Okay? So 200 joules. Okay? Now, a kilocalorie is a kilocalorie would be 4 kilojoules. Okay? A kilojoule is 1,000 joules. So let me get this right. 200 times 5. Okay? So 5 of those would be 1 capital C calorie. Okay? And you got 120. So 5 times 120, 600 lifts from the ground to the thing to burn up that 120 calories of thing. That's what we're talking about. That's unbelievable, isn't it? A piece of pie, you'd have to push a car for quite a ways to burn off that. But, of course, you're using it for other things, too. Most of what you're going to do is use that to just produce heat while you're sitting there, because you're always producing heat, because you're exuding heat. You know, you're at 98 degrees, right? Something around there. And the room is at 72, so your body is always burning calories, okay? So you don't have to lift that many weights. Just hanging around is going to burn a lot of that for you. But that's what it would be equivalent to. Yeah, pretty amazing. Okay? Now, you had two things. You had, when you're involved in heating, you can't have a temperature change. You know you're heating something up if the temperature is changing, right? Okay? Now, the more mass you have, the more energy it's going to take to heat it up. You also have the type of material. Different materials require different amounts of heat to produce the same temperature change. Now, I was at a physics meeting once, this was several years ago, and one of the schools had brought this setup. It was pretty nifty. They had a Bunsen burner, you know, all those little flames with the blue, things with the blue flame on it, and put it under, and they had a plate. I'm guessing it was about this big, probably stainless steel, I don't know for sure, but some type of plate there, and they had little holes drilled all around. It was a thick plate about like that, little holes drilled all around. And they passed out to us various pieces of metal, pegs, a lot like golf tees, right? Pegs that fit perfectly into those little holes. And all the pegs looked the same, except they were different colors because they were different types of metal. Somebody had aluminum peg, someone had a copper peg, someone had an iron peg, someone had a lead peg, you know, all sorts. They didn't have any silver and gold. I don't know why, but they just didn't have any of those. But they did have other pegs. You know, about 8 of them, it seemed like. They gave us each one and said, stick it in the hole closest to you and hold it until you can't hold it anymore. Because they had the Bunsen burner heating the disc, okay? So we put it in there and held it as long as we could, and finally one person let go, okay? Now, was that the biggest wimp in the group?
Yep.
No. And then after a while, someone else, and if you went to check it, the guy with the copper peg was the one who probably released first. Because copper, I'm just guessing now, has a fairly low specific heat, okay? And then the others and the others. Different materials require different amounts of heat to produce the same temperature change. And what you were measuring was the specific heat of the metals. The guy that released first, he had the one with the lowest specific heat. The guy that held on the longest, more than likely, had the highest. Now there was a wind factor in there too, but it wasn't really a major one. That measure is specific heat. And all three things go into displayed here. The amount of temperature change, the mass, and the type of material. The type of material is dealing with specific heat. Here is the equation that relates it. Not yet. It's going to get there. Get to that in a minute. Here's an example of that. Here is 10-gram block of aluminum. Okay? Okay, not very big, and it's at 20 degrees Celsius. What's 20 degrees Celsius approximately? No, just tell me in everyday terms. What's 20 degrees Celsius? What did you say? Not 40. A lot more than that. So again, 20 degrees Celsius. Okay? It's about room temperature. We're right about 20 degrees Celsius right now. We're probably, 71? I can't read that. Is that right? 72, okay. 20 degrees Celsius is 68 degrees Fahrenheit. So, about room temperature. And bring it up to 100 degrees Celsius, what's that? Boiling point of water, not of aluminum, but it's the boiling point of water. So you've taken a pot out of the thing, an aluminum pot, put it on the stove until water starts to boil. You have done that, okay? In order to go that way, you have added 176 calories to be absorbed because the specific heat of aluminum is 0.22 calories per gram degree Celsius. You have 10 grams of specific heat of 0.22 calories per gram degree Celsius. You change to 80 degrees, that was 176 calories absorbed. If you had 10 grams of copper, copper is a lot denser than aluminum, so it would be a smaller block, but it would still be 10 grams of copper. That has a specific heat of only 0.893. Okay? Now, if we had gold, its specific heat is 0.03. Now, gold is even denser than copper, so that would be much smaller, but it would have that. If we had a gold peg, he would release it first, but he grabbed it and run for the door. No. Just kidding. Okay. That's why they didn't know. So, that's only 24 grams absorbed for the same change of temperature. Same change of temperature, 74 calories. Same change of temperature with aluminum, 176 calories. See, that's almost quite 20, more than double. Okay, more than doubled here, and this is more than triple here. Okay, so yeah. Now that could go either way. That's the number of calories absorbed to heat it up, or the number of calories released to cool it down. And both of those would be equivalent. So what's our equation? Summary in the equation is this one. Q. Now in this chapter, capital Q stands for heat. Capital Q stands for heat. Generally measured in calories, but it could be kilocalories, it could be BTUs, it could be joules. Whatever you're using, that's heat. M, of course, is mass. C is specific heat, the symbol for specific heat. Now, they use C for a lot of things. Speed of light is C. Not in this case. Here you're talking about heat, so that's specific heat. And then delta T would be change of temperature, temperature change. Delta means difference in it, or change in temperature. So this would be a delta T of what? 80 degrees, exactly. And your mass was 10 grams. Specific heat, 0.22 for aluminum, 0.093 for copper, 0.03 for gold. Okay? There's your formula that does it. Now, this has three factors over here. So what you could do, if you knew the specific heat, the total heat, the specific heat and temperature, well, know how much mass you have, divide this by these two, and that gives you mass. Divide by these two, you get specific heat. Divide by these two, and you get change of temperature. So you actually have, 4 equations that are all equivalent. Okay? Any questions? on specific heat. I'm trying to keep up with, whoa. Let's back up a little bit. Okay. I neglected to do example 4.4 and, oh, we only have 4.4. Okay. What's that? No. Okay. Example 4.4, back on page 94, somewhere thereabouts. A 1,000 kilogram car. What's that a measure of? Okay, what color you want? I need a light color for this dark brown background. Say again? Green. The light green I think will show up pretty well. Okay? I think it will. Okay, so this is a 1,000 kilogram car. Is that okay? What's that a measure of? That's the mass of the car. Okay? Oh, and it's not just 1,000 kilograms, it's 1,000.0 kilograms to the nearest tenth of a kilogram. That is a very specific car. It weighs exactly that amount. Is moving at 90 kilometers per hour. What's that a measure of? That's the speed or velocity. Okay, good. Okay. Now they also tell you that is 25.0 meters per second. That's the one we're going to use. Okay. That's smaller units than kilometers per hour. How many kilocalories are generated when the car brakes to a stop? How many kilocalories are generated when the car brakes to a stop? How are you going to do that? What kind of energy does that car have? If it's moving at, it's what? That's kinetic energy. And what's the formula for kinetic energy? 1/2 times the mass times the speed squared. And we got everything we need. That's 1/2 times 1,000.0. That's ridiculous, but we'll put it. And then the speed is 25.0 meters per second, but we're squaring that part. So rather than carrying around this anymore, I'll take half of 1,000 and make it 500. Okay. Kilograms probably should be a 0.0, but who cares? Times, and anyone know what 25 squared is? Got it? 625, you're absolutely right. 625 meters squared per second squared. When you square the number, you also square the units. Then 500 times that would be 3. Say again? 3125, yeah. Okay. And I got to clean that up a little bit. Oh, that's the wrong key. Sorry about that. Sorry. Go back. It was 312,500. 312,000 little c calories. Oh wait, I'm sorry. No. Okay. Wait a minute. You got to think. What were our units? Kilogram, meter squared, per second squared. That's measured in joules. That's 312,500 joules. Yes, change that to kilojoules. That would be how many? 5 kilojoules. Okay. Now, calories, how are we going to do that? Multiply that by, say again? Yes, very good. Let's get our units in place first. What unit goes where? What unit goes where? Numbers go here, units go there. Always put the units in the place. Which one goes where? One goes on top, one on bottom. Kilojoules or calories? Which one? Okay. We got two units, kilojoules and calories. Which one goes on bottom, which one goes on top? Huh? Say again? No, if you put kilojoules on top, multiply it, you have kilojoules squared per calorie. That's not going to work. It's calories. Now that's capital C calories, which is kilocalories per kilojoule. That way your kilojoules cancel out. You see? Now, what was our conversion factor? You said 4.124, I believe it was. But 1.8, yeah, 4. What was it? That was 1. Okay. Let's go find the thing. I know it's in the book. I just can't. Oh, here it is. Here it is. I thought it was 94 at the top. That's where I was looking. I just can't see it. There it is, right there above there. Yeah, 4.184 what? Joules. Okay, 4.184 joules per 1 calorie. And that would be 4.184 kilojoules for 1 kilocalorie, which is a capital C calorie. So that's why I've done it this way. So you take this and divide by that. 312.5 divided by 4.184. What do you get? Okay. Okay. All right. Let's go back and, okay. 4.184 joules is 1 little c calorie, right? And then kilocalorie is 1,000 little c, so that's be a kilojoules. So I just did one conversion. Okay, but then you'd have little c calories. Well, what is the question asking for? I've lost it now. How many capital C kilocalories? That's what we're looking for. So make this kilocalories. Make it little c calories, but make them kilocalories. Now the kilos could cancel out, so you're still okay. What would that be? 312.5 divided by 4.184. Something short of 80, isn't it? 70 something? Yeah. 74.7 is what the book has. Now, I don't know why they went to all the effort to give you 1,000 kilogram car with a decimal point after that was what? 5 significant digits there, but then the speed was only 3, so you round to 3. So yeah, 74.7 kilocalories. Okay. Now let's think about what it was. That's how much for the brakes to stop. Okay. That was capital C calories. 74. So if you had drunk, okay, you should have been able to stop that car moving at 90 kilometers per hour, a 1-ton car moving at about, 90 kilometers per hour is around 65 or so miles per hour. You should be able to stop it from the energy you got from drinking that. Okay, that's unbelievable, isn't it? Yeah, that's the amount of his drink, his green tea drink was 120 calories. This is less than that. Okay. Now, where is that heat? What happens to it? Yeah, it's lost to the atmosphere, but if you were to touch the brake pads, you'd find out that's where the heat is, because those things are hot, right? Very, very hot. Okay.
So in other words, my drink is
Yeah, once you drink it, yes. Right. Okay, the energy from that drink would have been more than enough to stop the car. Yeah, try it. No, don't. Okay. Okay. So there was specific heat. There was our equation. Q standing for heat. Okay? Now, what's that? Yeah, we're not going to do that. No, I'm not saying it, but that would be the energy that would be taken. Unbelievable. Okay, let's look at example 4.5. How much heat must be supplied to a 500 gram pan, 500, actually 0.0 gram pan, what's that a measure of? Mass of the pan, to raise the temperature from 20.0 degrees Celsius to 100.0 degrees Celsius. What does that represent? Okay, and what would that be? That would be your delta T, and what would that be? 80.0 degrees Celsius. That's your delta T. If the pan is made of iron. Okay, now time out for just a moment here. You would almost have to read the chapter to get all this. But actually in table 4.2, now before I go there, when we're picking up that other thing, I wanted to point this out to you, and I just sort of skipped over it because the slideshow left it out, but it is pretty important stuff. When they were talking back on page 94, the same place we got the what they call mechanical equivalent of heat, okay? They had some other equivalents there, I think. Well, I thought they did, but I don't see them here. That's on page 96. But before we got there, I thought they had here the other equivalents laid between BTUs and calories and that kind of stuff. And I guess they don't, which is a shame. They really ought to have those in here too. Sorry about that. Those of you who have one of the old books that has it in the front, they do have those. 1 BTU is 252 little c calories, okay, which means it takes about 4 BTUs to make 1 capital C calorie, okay. Not quite, but close to it, okay. So I thought they were going to show them back there, but they don't. I don't know. They used to have tables in the earlier editions. They don't have them anymore, and that's a shame. Okay. So let's get back to 4.5. Oh, what I was going to say is turn to table 4.2. Now, this is in all your books. I don't know exactly the page number. In mine, it was page 96. It's going to be somewhere plus or minus from there. Let's look at some of the common specific heats. Okay? We saw, let's go back to this one. Oh, I'm in the wrong place. Yeah, this one. I know I've written on some of that. Specific heat for aluminum was 0.22, copper was 0.093, and gold is 0.03. Look at some of the other. Air, specific heat of air. Now, most of the time we talk about specific heat of solids. You can do liquids and you can do gases, and air would be 0.17, okay? Aluminum, as you saw here, 0.22. Concrete, 0.16, so it's a little bit less than specific heat of air, but pretty close to it. Copper, 0.093, we saw. Glass, on average, 0.160, so that's about the same as air, about the same as concrete. Okay. Gold, 0.03, we saw that one here. Ice, 0.5. That's bigger than anything else in the table so far. Ice, 0.5, specific heat. That many calories to raise 1 degree of ice 1 degree Celsius. Half a calorie. Okay? Iron, 0.11. So it's half that of aluminum, a little bit more than that of copper. Okay? Lead, 0.0305, that's awfully close to gold. Mercury, 0.033, again pretty close to gold. These dense metals are pretty low specific heat. Seawater, 0.93. Look how big that is. Nothing else has come close. The closest to it is ice. Silver, 0.056, a little bit better, higher than gold, but not as high as copper. Soil, on average, because soil's a whole other mixture of things, about 0.2. So not far off from aluminum. Guess what? A lot of soil particles contain aluminum or silica in them. They're about the same. Steam, look at that, 0.48. Close to ice. And not as much as seawater. And then water, 1. Well, of course it has to be 1. Why? Because it takes 1 calorie to raise 1 gram of ice, 1 degree Celsius. That's our standard. Water is usually standard in everything. But water, of all the materials listed in the table, gases, metals, liquids, whatever, nothing comes close to water except seawater, and it's a little less. Ice, which is about half. Steam, a little less than half. Water, and ice and steam are made up of water. Water has one of the highest specific heats of any substance on the planet.
Other than salt, what does seawater and water have different?
What you say?
Other than salt, what does water and seawater?
That's mostly it. It has dissolved salts in it. That's just about the only difference. And they decrease your specific heat just about a little bit. Now, what is a ramification of the fact that water has such a high specific heat? How do we use water? You guys should know that. Yes, exactly. That's why we use it to cool your engine. If you put vinegar in there, if you put mercury in there, nothing else would work as good as water. Water will absorb more heat per gram per degree Celsius than any other substance. The only one I've seen higher is helium, but helium's a gas and it's not very common. So, and it's just 1 point something. But water, for all common materials, water is the highest specific heat.
So why do you need antifreeze?
Good question. Why do you need antifreeze?
Freeze.
Okay, yes. In the wintertime, when things get below freezing, water is going to freeze at 0 degrees Celsius or 30 degrees Fahrenheit.
So
Yeah.
this time of year we really don't need it.
You don't need it now, except for the other thing. What else do they put in antifreeze that's helpful?
Keep down.
Yes, keep down with rust. Is that what you said? Yeah. They put materials in there to retard rusting. Water at high temperatures is going to really rust metal pretty quickly.
Till your neighbors die.
Yeah, it will, because antifreeze has glycerin in it, and glycerin is a sweet-tasting substance, but it's also not good to drink. And so,
Glycol.
what's that?
What's the antifreeze that like will kill somebody? It's something glycol.
Yeah, I don't remember which, but see,
So you change
that's
it.
from glycerin. It's an alcohol of glycerin, basically. Yeah. Second.
I said they changed that now.
Yeah,
They've made it where you won't kill
Yeah.
dogs and stuff.
yeah. But it's still not good for them to drink. So
Yeah.
they try not to make it sweet-tasting, so it's attractive to them. What's that? Yeah.
A lot of that.
Yeah.
Okay, so we use that. Now, if you think about other things, this time of year, getting really hot out there, air has a fairly low specific heat, soil has a fairly low specific heat, but water has a pretty high specific heat. And my wife's family used to love to go to the beach in the summertime. And, I don't mind it, but beaches are my favorite place, but when you were driving south in the heat of the summer, the further south you drove, really, the hotter it felt like. Montgomery was always pretty miserable feeling. Keep driving down, just kept getting hotter and hotter, not by much, but a little bit. But then, about the time you get real close to the Gulf, it feels cooler. Why? Okay, the breeze is one thing. The water, because water has a higher specific heat than the land does, so more of the water absorbs more of the heat from the sun, keeping the temperature down. The soil and the air, it doesn't take as much heat to bring that temperature up, and it gets hotter. It surely does. But you might notice at night, too, the reverses, because in the, it takes, the water hangs on to the heat longer, so the air temperature and the soil temperature will cool off faster. Water stays a lot more regular. So basically, the Gulf of Mexico acts like a big air conditioner for us. Keeps us a little warmer in the cool times and a little cooler in the hotter times. And that's what makes it nice. You mentioned the wind. The fact that you have those temperature differences, that's what creates those winds. Because if you think about it, where does hot air go? Up. So when the air on the soil, on the pavements, on the ground and stuff is heating up, it moves up. The cooler air off the ocean or the Gulf of Mexico comes sweeping in, and it makes it, you're right, that breeze coming in. But at nighttime, it goes the other way. And when in the old sailing ship days did the ships leave port? Usually at night, when the wind would be going out, cooler on land, warmer on the water, that would go up, and the breeze would take them out. So a lot of people got the idea that the fishing was better at night. That's why they went out at night. Well, no, that's actually, it's a lot easier to go out at night. Okay. But don't tell your parents. Okay. So that's specific heat. That was, so I was telling y'all that about the table. We needed to go back to the table to get the specific heat. Let's go back one. Iron. Okay? Now, notice what we've got here. We've got the mass here. We got the temperature change here. We got the type of material here. What does the type of material influence? What is the thing that we use to measure that? To indicate different type of material? Second? Specific heat. Yeah, and what is that? C. Specific heat for iron. Iron is Fe. What was that in our table? .11. Well, just to keep the units of calories, okay? 0.11 calories per gram degree Celsius. Okay? Now, what was the question? I got off onto that. How much heat? Okay? Remember what our equation was? It showed up down here, but yeah. Okay, yeah, okay. But what was that equation we used? It shows up. Yeah, Q is equal to MC delta T. Q is the heat. That's going to answer the question. M is the mass, which was 500 grams. C was 0.11 calorie per gram degree Celsius times delta T was 80.0 degrees Celsius. Now look at your units. Grams go out, degrees Celsius goes out, and you're left with calories. That's a good thing to measure heat in. So 500 times 0.11 times 80. What do you get? 4,400 calories, or if you wanted to use a, 4.4 kilocalories, is that what you're saying? 4.4 kilocalories. If you want a smaller number with a larger unit, move the decimal 4 places. Now, in reality, they probably are going to keep not 2 digits, that's all you got here. 4.4 kilocalories. Okay? Well, that's if it was iron. What if that were, what was the second question? Aluminum. So what would that be? B would be aluminum. So what would that do for it? Yes, it doubles it because that's twice specific heat. That would be twice the amount of heat. So that would then absorb 8.8 kilocalories. So it's going to take more heat to heat the aluminum than it does to heat the iron. And that may be one of the reasons that a lot of people love cooking in cast iron, because it's going to heat up a lot faster than the aluminum pot would. That is if they're at the same mass. Yeah, aluminum's a lighter metal, so you can have them.
So you can use an induction cooktop or
Right.
whatever you cook on.
Now, even I thought you were going to say this, and a little bit earlier, they had the pans that were aluminum at the top, but copper on the bottom. And look at copper; it has even lower specific heat. So yeah, those kinds of things, yeah, you have begun doing. So there we have example 4.5. Let's move to 4.6. I think we can erase this. Everybody got it? Okay. 4.6. What is the specific heat? This time we're looking for what? Specific heat is Q. No, heat is Q. Specific heat is C here. Okay. What is the specific heat of a 2 kilogram piece of metal sample? That is 2 kilograms measures. 2 kilograms measures mass. Okay. If 1.2 kilocalories, what's that a measure of? That's your Q, heat. You're absolutely right. Is needed to increase the temperature from 20 degrees Celsius to 40 degrees Celsius. That's a delta T of 20 degrees. Okay, there's your delta T. We're looking for C. What you reckon? How are we going to get that? Rewrite the formula. What was your formula? Q is equal to MC delta T. Very good. If you're solving for C, you do what? Yeah, divide both sides by M delta T, and that way you get C. That's it exactly. So this will be Q divided by M times delta T. Well, your Q was 1.2 kilocalories, and your M was 2 kilograms, so you can do that as long as the K's are the same. Okay, that's good. Kilo mean 1,000. 20.0 degrees Celsius. Say again? Okay, don't change that. Leave it 1.2 divided by 40. .03, it would be kilocalories per kilogram degrees Celsius. Oh, okay. And you had 2 kilograms of that metal. Let's look up and see what metal that was. 0.03. Oh my goodness, let's get out of Dodge, okay. Because if you have 2 kilos of gold, you got school paid for, I think, okay. No, I'm just kidding. Okay. All right, he's too literal, isn't he? Okay.
2 kilograms of gold. That really wouldn't be that.
Do you know what they measure gold in?
I'm talking about like, I mean, I know it'd be like a lot of gold as far as money wise. I'm talking like the size.
Right, yeah. It wouldn't be very much. You're right. This book is about 1 kilogram. And so it wouldn't be 2 books because this is not nearly as dense as gold, but it would be a nice sized plot. Okay? Probably.
Cheese commercial for the guys in the aisle at the grocery store. We got a fire going.
Oh,
Cheese. How much money would that be?
okay. What is gold selling for now? Several $100s an ounce, I think. What, $200, $300, $400, $500 an ounce? I don't know. Someone probably can look it up on your phone. What's the price of gold? It's a lot, yeah. Okay, but we found out that material was gold. And notice here, specific heat is sort of similar to density. If you know the specific heat of material, you have a pretty good shot of figuring out what that material is. Specific heats are a little closer together than densities are, so density is still a better measure. Here's a little bit of concepts applied here. They call it kitchen physics. We've just been talking about it. It's easier to change the temperature of metals with low specific heats than it is with high specific heats. So they were looking at the different types of pots and pans and what would be the most energy efficient to use. So, again, pretty good stuff. All right. Now we're ready for heat flow. Now let's think about how things are going today. We have the test the last 30 minutes, and we'd like to have the lab the previous 2 hours. We're coming awfully close to that, and we haven't quite hit enough material for the lab. So either we're going. Let's tell you what we'll do. Let's skip heat flow for right now and come back to it, okay? Because that's a fair amount of stuff there. And let's move to heat, energy, and molecular theory. And that's where we'll hit the last part we need. So we're going to come back and hit heat flow in a minute. That's important stuff. Let's hit this first, okay? Heat, energy. So we're skipping 4.3 for now so we can get the lab in today. And then we'll come back and do heat flow after we, next time on Thursday. All right, heat, energy, heat, and molecular theory. There are 2 responses of matter to heat. We've talked about one in particular. Okay? You heat something up and what happens? Temperature increases. And that's what we usually think of happening, isn't it? Heat goes mostly into internal kinetic energy, which changes the temperature, right? Okay. To measure that, we use specific heat. How much heat does it take to raise 1 kilogram, 1 gram, 1 degree Celsius of that material? Okay, to increase that by 1 calorie. But there is something else, and we have done this, and you may not have thought of it. We were adding heat in that last lab, weren't we? And the temperature wasn't changing. What was happening? The ice was melting, or the water was, once it started boiling, what is boiling? Evaporating, exactly. Then you are changing phase. Okay, well here's what's happening with when you're heating things up. The molecules When they're very cold, they move slowly. When they heat up, they move more rapidly, and then they move even more rapidly. So here's what's happening. Energy is, when you're adding energy, you're going this way. You heat that ice. Now, can you heat ice and it not melt? Okay. Have you ever had your hand just a little bit wet, reached into the freezer to grab a cube of ice, and then you have trouble getting it off of your finger? What's it done? It froze the water that was on your finger. It didn't melt, but it's heating your hands hotter than the ice. You're increasing the temperature. Okay, I wondered who was going to bring it up. Okay, make some more. No. The movie, what was it, Christmas Story? Was that it?
Yeah, put his tongue on the pole.
Put his tongue on the pole. Now, actually, this is our favorite story to tell my brother-in-law, especially if his kids are around. I haven't told you this one, have I? Okay. My wife's brother's 4 years younger than her, so she was off doing something else. But her mom had her little brother and then her little sister, who's 2 years younger than him, in the grocery store with her one day. And it was hot summertime, and that she was picking up a few things sort of in a hurry and wasn't really paying close attention to the kids. And she was getting about ready to check out, and she said, "Terry, where's Keith?" Now, Keith, you got to get into Keith. Keith is this Mr. Swaven the Boner. I mean, he's tall. No, never mind. Suave and debonair. No, never mind. My uncle used to say that. Okay. Tall, good-looking, basketball player, pretty smart, Mr. Cool. Huh?
You're talking about the kids, right?
Yeah, they were kids then, but he still thought he was decent work, But anyway, but this is why we like to tell it on them now, because he's this other stuff. Mr. GQ magazine type thing. I mean, he has all the fanciest, all this kind of stuff. Okay, so, especially if his kids are around. So she said, "Terry, go find Keith. Yeah, we need to get home. This stuff's going on." So she went back and was looking for him. She saw him bent over the ice cream thing. And she said, "Keith, come on, Mom's ready to go." He said, "Terry, look at that Mom." She said, "What?" She said, "Look at Mom." Okay. So she ran to get her mother, and see, he's back there at the ice cream thing. Of course, the frost had built up on the cooler there in the stores, and he thought, "Oh, it's such a hot day. That looks so cool," and he went to lick the ice. He got his tongue stuck on the ice, and his mother was so mad. He thought, "Oh, how nasty. My child has his tongue on this ice." I don't know if she's worried about his nasty germs on the ice, the other people handling. I don't know which way, but she just grabbed him by the scruff of his neck and yanked. Blood everywhere. Got him out of the store, stuck something in his mouth. He was screaming bloody murder, stuck something in his mouth, checked out, and left. It was terrible. We love to tell that on Keith, What's that? He healed okay, but it was not pleasant. Exactly, but she wasn't. Probably wait until she got home to do that, and she didn't want to do that in the store. Yeah, well, she did, but anyway. Anyway, that's what we've got going here. You can warm ice, add heat to ice, and raise its temperature. But then once you get to a certain place, then it starts melting. Until all of the ice melts, it stays at that same temperature. That's called the melting point, or the freezing point if you're going the other way. But then once it all melts, it becomes water. Then you can increase, and you see ice, when it's ice, it's in that crystal structure. Okay, it stays in there, increases its average kinetic energy, the molecules move faster. That means it's raising temperature. But then when it melts, then the molecules are free to move around. That's in liquid phase. Okay, water. And that's what's happening here. As long as there's ice and water present, it's still at the same temperature. Once all becomes liquid, then the temperature starts increasing again. Then once it reaches the boiling point of water, now you add more energy, and now you're freeing those, breaking those, that proximity, that cohesion that it has, and now they become gas molecules, steam. And that's what happens there. And as long as there's water and steam, it's not changing temperature either, even though you're adding more heat. You're just freeing more molecules, okay? And that's the evaporation process, okay? So, two things go on with the response to heat. Things increase in temperature, or they change phase. Phase change at the constant temperature. Say that again.
You make a water heater without heat.
You make a water heater without heat.
Kind of like you air conditioning, you cooling the water without, you just removing the heat.
Yeah, exactly right. Yeah. And
you do the same principle for a water heater, the opposite.
okay. I don't know if this is exactly what you mean, but when you have steam, if that steam is condensing to be water, you're actually releasing heat then, okay? And you can, in fact, you can burn yourself with steam a lot worse than with hot water, even if they're at the same temperature. Steam will burn you worse at 100 degrees Celsius than boiling water will at 100 degrees Celsius, because it has the, and we're going to get to that in just a minute, that's called the phase change. At a constant temperature, you can add heat to it as long as there's two phases there. It's going to stay at the phase, change to the higher level or lower level if you're going the other way. It's related to changes in the internal potential energy, and that's called latent heat, not specific heat. Latent comes from the word that meant hidden heat. And that's why steam can burn you worse than water, because it has not just specific heat, it also has latent heat. And these latent heats are really, really high too. Okay. Here is the diagram that shows this, and this is a pretty good graph. Like we were saying before, if you have ice down here at minus 20 degrees Celsius, very, very, very cold ice. That's colder than your freezer. The freezer's usually maybe minus 5 or minus 10. This is way at minus 20. You add heat to ice, all it does is warm the ice. It doesn't melt it.
Well, what's dry ice?
Okay, dry ice is actually solid carbon dioxide. You've cooled carbon dioxide until it actually goes directly from gas to a solid. It doesn't go through the liquid phase at normal temperatures and pressures. It goes lower. So dry ice is solid carbon dioxide.
So first you gotta make carbon dioxide.
Yeah, you have carbon dioxide, and then you drop the temperature, drop the temperature, and then it becomes what they call dry ice. And that's very cold stuff. You don't want to mess around with that. Okay. Okay, you warm that ice, all it does is change temperature. Up until it gets to 0 degrees, and then you add more heat to it, then it doesn't raise the temperature, but it starts melting. And as long as there's ice present and water present, the temperature doesn't change, even though you're adding heat. And it's adding heat, but it's not raising temperature, it's just changing phase from solid to liquid. Until all of it melts, and then you add more heat, now the temperature starts increasing again. And by the way, this is a specific heat down here of 0.5. Remember, ice specific heat is 0.5. Okay, we'll get to the phase change in a minute. Here, water specific heat of 1. The highest of just about anything. 1 for every gram of heat, a calorie of heat you add, it increases the temperature 1 degree Celsius for every gram of liquid water you have. And you keep heating it up until you get to 100 degrees, and at that point, adding more heat doesn't raise temperature in. So when you're cooking your food, once the water starts boiling, there's no reason to keep the heat up. Cover it, drop the heat just as long as you can keep it boiling. It's going to cook just as fast. That extra stuff is just boiling more water out. You know, it's just changing phase. It's not adding any heat, adding any temperature. It's just adding heat. So as long as there's water and steam both present, it's going to stay at 100 degrees Celsius. That's what happened in our lab, and that's the boiling point of water until all the water boils away, and then that pot will start getting hotter. And now you've got steam, and now you're heating the steam. Here the steam was at 100 degrees, now you start. This was 0.48, was specific heat here. So let's talk about what those latent heats are.
So if you still in the kitchen,
Say again?
if you boil a vegetable or steam a vegetable, you can steam it quicker than you can boil it?
Generally, yes. Okay, because that steam has more heat than the boiling water does. You're absolutely right. Because you don't just have the caloric heat, you also have the latent heat. Okay? And that's why they do it. Now, it's probably not, in some senses, quite as efficient. Let's look at what those numbers are, and here's the phase changes. The latent heat, we call it the latent heat of fusion when it goes from a liquid to a solid. We usually call it the latent heat of melting when it goes from a solid to a liquid. But they're the same heat, latent heat of fusion, latent heat of melting. We call that temperature is the melting point. At that temperature, there is no change in temperature until all the solids become liquid, all the liquid becomes solid. Fusion or melting. But if you're going the other way, this is if you're going from solid to liquid, it's the melting point. From liquid to solid, it's the freezing point. It's the same temperature. It's just which way you do it. No, the heat's going up. The temperature's staying the same. But the heat, increasing heat is melting, decreasing heat is freezing.
So what's that first block? Is that a temperature
Okay.
greater, temperature less?
Right, okay. Really, what this is heat. It's not really temperature.
It should say heat, right?
Yeah. Because latent heat has no temperature change. This is heat change. They really should, you're right, they should put heat there, not temperature. Now, liquid to gas, we call that the latent heat of vaporization. Now, you could call it latent heat of condensation if you're going from gas to liquid. It's the same value, okay? It's a boiling point. If it's going from liquid to gas, it's called the condensation point if you're removing heat and it's going from gas to liquid. Now, you can also go from a solid to a gas, and that's called sublimation, and it's called the heat of sublimation, and going either way, it's called sublimation. Have you ever seen a solid sublimate? Sublime? You may not have actually watched it, but you've realized it. Remember the old refrigerators? You put your water in the ice trays, and you had the ice cubes. If you didn't use those ice cubes for several weeks, what happened to them? They get smaller. That ice actually went straight to the gas. It didn't melt necessarily. It went to a gas. It sublimed away. Especially in frost-free refrigerators, where they are trying to keep, they're subliming the ice off the frost, so you don't have frost in your refrigerator. It's also doing the same thing on your trays. So that's the sublimation point. It's just the molecules are moving faster, but there's a graph. I think there's a name for it. I can't think of it, but there is a point where it's called the triple point, where any material will be a solid, a liquid, and a gas at the same temperature. It varies by pressure and things, and vapor pressure and other things are involved with it. And if you adjust that, just so you can go straight from, at the triple point, all three exist, but most of the time it's liquid to solid to liquid, liquid to gas. But The closer to that you get, you can go from a solid to a gas or a gas. You don't usually go from a gas to a solid. It doesn't do that way, but it will go from a solid to a gas. And that's called sublimation. And that's what dry ice is doing. Dry ice, as you cool it, it goes straight to a solid. It doesn't go through the liquid phase. And then when you release that, y'all been to rock concerts where you had all that smoke around there? That wasn't smoke. That was dry ice scattered around there, and as the dry ice evaporates or sublimates from the solid to the gas, at a very cold temperature, and all the moisture in the room now starts condensing, and you have fog. And that's all that is. As soon as the temperature rises, it disappears. So that's how they do that in concerts and things. Okay, I think that's probably all we need for the lab. We'll go back over this later. But I did want to give you the quantities there. The latent heats. And I don't know why they don't put them on the slides, but they don't. Okay? Here is the formula for the latent heats. Let's go back to that. The latent heat. Where is the best place to put it? Yeah, right here. Remember what was our specific heat formula? So let's go back to this one, specific heat. What was that formula? Q is equal to? Say again?
Heat.
Q is heat. And what was it equal to? What's the other side of the equation? MC delta T. Mass specific heat. This is specific heat. Okay, and change of temperature. Okay, for your latent heat, there's two. Latent heat of fusion, that's going liquid to solid or solid to liquid, either one. That is M L. Let me make sure. Yeah, I'm sorry. I've written it backwards. Sorry about that. This is Q, again, the heat transfer, M times latent heat of fusion. Okay. And for ice, I know this is in a table somewhere. Oh, there it is. It's on page 102 in my book, somewhere around that for yours. The latent heat of fusion for water is 80.0, I think it is, calories per gram. Whereas specific heat was 1, or for ice is 0.5, or for steam is 0.48. For latent heat of fusion, 80 calories per gram. Now, if you're talking about vaporization, that's even more. Q is equal to M L, goodness gracious, I can't write. LV, latent heat of vaporization. And that one, that is your mass times 540 calories per gram. Now notice the specific heat was calorie per gram degree Celsius. The latent heat is just calorie per gram, calorie per gram. Why don't we have degree Celsius in there? The latent heat, there is no change of temperature. Remember, that's at a constant temperature, the freezing point or the boiling point. So that's why there's no degree Celsius, it's just calorie per gram. Look at that, latent heat of fusion, 540 calories for every gram. Okay? Pretty big. Okay. That's all we need, I think, for the lab. We really would be good to do this. Let's do this example 4.7. I think that would be worth it. So let me get rid of this. And let's do 4.7. How much energy, what's going to answer that question? What variable? How much energy? What variable we use for heat energy? Q. So Q is the unknown here. How much energy does a refrigerator remove from 100 grams of water? That's a measure of what? That's the mass of the water. at 20 degrees Celsius, 20.0 degrees Celsius, sorry about that. Okay, to make ice, this is liquid water, to make ice at minus 10 degrees Celsius. How much heat does it take to do that? You can't answer this question in one step. You got, yes, you're absolutely right. First thing you've got to do is cool the water. So the heat of, I'll just call it cooling here. What process is that which changes temperature? Which kind of heat? Say again? Okay, yeah, calorie is the unit will you be using, but what is the process? What? We're going from liquid water at 20 degrees to liquid water at 0 degrees. Like you said, you got to first cool the water. So that's using which kind of heat? Not latent. You're not changing phases. You're changing temperature. So you use. Yes, you were. Specific heat, because that has a change of temperature in it, right? So that's the formula you use. Whoa, I'm going the wrong way. Where is it? There it is, okay? So the first we do the cooling. So you use specific heat. MC delta T, because we have a delta T going from 20 to 0 degrees. Okay? That's your delta T, and it's still liquid water. So you use the mass of what? 100.0 grams times, what's C for water? 1.00, what units? Calories per grams, degrees Celsius, times delta T, 20. You change it from 20 to 0, so that's a change of 20 degrees Celsius. So your grams go out here, your degrees Celsius goes out here. How much is that? I can't hear. 2,000 calories, is that what you said? Absolutely. 2,000, my hearing's so bad. 2,000 calories, okay? Or 2 kilocalories, exactly. What's the next thing you got to do? Not yet. What happens first? That is liquid water. Liquid water at 0 degrees, but it's still liquid water. Say again? Now you got to freeze it. So this is QF, the freezing of the water. What formula do you use for that? C, no C in it. ML, that's it. Okay? And that's latent heat of fusion, so it's MLF. Okay? And your mass is still 100 grams. Okay? And what's the latent heat of fusion? 80 calories per gram. So the grams go out again, and that's how much? 2,000? 8,000. 8,000 calories. Wow. That's to freeze it. Okay? But that only gets it frozen at 0 degrees. So what you got to do next? You got to cool it again. So what formula do we use? MC delta T. So can we just write down the answer? What we did last time? Why not? Say that again. Oh yeah, it's a different temperature, but okay. You're changing now. Now you're changing from 0 degrees to minus 10 degrees. So your mass is still 100.0 grams. But what's your C now? Yes, because it's a different specific heat. Ice has a different specific heat from water. 0.5 calories per gram degrees Celsius. And your temperature is also different. It's a 10.0 degrees Celsius. Okay? So the grams go out, degrees Celsius goes out, and how much is that? 500 calories. So the whole process was 10,500 calories. And where was most of that spent? Changing the phase, freezing that water. If you had been evaporating the water, then rather than 80, it's been 540. Big time change of heat. Okay, so remind me next time, we're going to start with heat flow. This is where we're going to start next time, heat flow. Then we'll skip, because we've already done it, we'll skip the phase change, okay? But then we'll pick up with evaporation and condensation. So, y'all going to have to help me remember that. All right, we're going to get ready to do lab. Do y'all want to go to the one we've been going to, 259? There's not as much lab surface space, so it's going to be a little more cramped there, but it's going to be, I don't have to move things as far, so the other labs are a little more convenient as far as having plenty of table space to work, but we got to move things more. What's that? I can't hear.
Whichever one's going to help us on this text.
Okay. Let's go on down to 259. That'll just be a little bit faster, perhaps. Okay. So, okay, 5 teams. There'll be 2 people per team. 1 team will have 3 people. Let's see. The time is now 4 o'clock. So Carrie got here for the second half. Let me go to Mark roll first. James is still here, right here. Okay. Terrence is still here. Camp is still here. Slim didn't make it in today. Dart is still here. Yep, right there. Mason's still here somewhere. Aren't you? Okay. All right. Samuel's still here right there. Whoops, I just marked you for Dart. Okay. Ryan's still here. Alfred's still here. Jeremy's still here. Charles is still here. Brittany hasn't made it in yet. Trevor hasn't made it in yet. And I got Terry here. So we got 10 now. 2 per team, and whenever Mason comes in, he'll join one of the teams. Okay? Second?
I thought you said 5 people per team.
No. 2 people per team, 5 teams.
Oh, I thought it's actually 5 teams of 2 if we got 10 people.
Yeah. Okay. So there's 5 stations set up. Find one of the stations, and some of the cups are numbered 1, 2, 3, 4. Some are not. The first cup is number 1, 2, 3, 4. Count from left to right. Some are not. Okay, 2 per team, 1 at each station. 2 per team. There's another station there that needs 2 people. Got 2 here, 2 here, 2 there, and 2 right there. Okay. And then whenever, yeah, right. Need 1 here. Yeah. Okay. I'll try to stay close to the computer. All right, I've got thermometers in each of cups 1 and 2. So measure the temperature in the 2 cups 1 and 2, and record that. Don't pull the thing out of the water. Don't pull the thermometer out of the water. Measure it while it's in there, touching water. Keep it submerged. Okay. Measure cup 1 and cup 2. What's that? Yeah, these are reading in Celsius. Okay? Now, when you've got those 2 measured, pour one way or another, but pour water from one of those into the other. If you got a small cup and big cup, pour the small into the big. If they're the same size, pour either way you want to. Pour, okay, just pull out the one you're pouring from and pour into the other one. Pour all the water into it. Yeah, you can leave that out for now. Put it in the cup 3 or 4. You're going to put it there later. Okay? Join one of these 5 teams, any one of them. Yeah, there's 1, 2, 3, 4, 5. Just go to any one of them. Okay? Measure the temperature of the mixture. Okay? Everybody got it? Yeah. Okay. Now move the 2 thermometers to the other 2 cups, 3 and 4. Once you've measured the mix.
Put them in the same cup.
Put 1 thermometer in cup 3 and 1 in cup 4. Okay, and when they come to equilibrium, measure the temperatures of those 2 cups. Okay? Do not mix yet. Just measure the temperatures. When every team has measured the temperature, then give me a heads up. Cups 3 and 4. You measured 3 and 4, right? Everybody got it? 3 and 4. Yeah. Now, before you mix, you estimate, once you mix 3 and 4 together, what's going to be the temperature of those 2. Whatever you want to do, you estimate. Huh? When you estimate, after you estimate, then you can mix. Okay, once you've estimated, then go on and mix them. And measure the temperature of the mix. Okay. You've estimated and you measured. Okay. Now the next is the question. And the question is, look at 1 and 3 and 2 and 4. Are those temperatures fairly close? Okay. Were the mixtures fairly close? As close as the temperatures of the originals? Yeah. They were? That's interesting. Let me see. Okay. Whoa.
That ain't quite. Well, yeah, because our cup 3 was 38, our cup 1 was 24.
Really bizarre. Everybody get that kind of difference?
Hey, no, they'll probably get sippy looking stuff.
Huh?
10 degrees different. Then we got what?
No, between cup 1 and 3.
Cup 1 and 3. 1 degree difference.
Okay, they got 14 degree difference. Let's y'all try it again. Okay, I'm glad you used pencil. Okay. Okay. Hold on a minute. 1
What was
and
y'all's
3,
top
right?
2 and 4?
2 and 4 is 14 and 15.
That's what we got.
Okay. Goodness, you had big differences too. No, you didn't. That only had degrees. Okay. Keep that
Well,
one
if you
together.
add this 57,
Okay, yeah.
that's 57.
Okay, yeah. You did over there. Okay. And they should have been. Now, there are some wacko thermometers here, so I'm going to have to check and see if you got one of the wackos. Remember, somebody had a thermometer that measured way different from the others, did you?
Well, I think our company did get different.
There's a thermometer right there. Can you get it for me?
I can.
Thank you.
I probably didn't take the. That's probably what happened. You take the thermometer.
What's that?
One of them brought it down, the other one balanced it out.
Okay. Just a second. This thermometer seems bad, so I'm just going to leave it alone. I gotta go get it.
We just need to check cup 3. Where's y'all's cup 124?
Right around the cup one, I could have won the score.
Oh, wow.
Okay.
We need cup 1 and cup 3 then, because both of our cup 1s and cup 3 were.
What's your cup three for?
Our cup 3 was 38, our cup 1 was 24.
My cup three was 42.
Everybody else had a much closer than y'all did, so.
Yeah, somebody go ahead and take the thermometer away from Sippy.
I think it was bad thermometer.
Can't grab the thermometer. Sippy don't
This
need
has
that.
got 9 degrees, everybody else is around. Okay, y'all do those again.
Don't let Sippy touch it.
When you hold the thermometer, your hand got to be the same temperature as the water.
All right, now for the rest of you, okay, I heard one comment going on back there and I wanted to wait until I had time to address it. So for the rest of you, your cups 1 and 3 were pretty close, right?
Right.
And 2 and 4 were pretty close.
Right.
Yeah.
Okay, usually no more than a degree or 2 apart, right? But your mix, were they as close as your others?
No.
Why not?
Because the first mix, we brought the temperature down because the temperature.
The first cup had more.
All right, there it is. There were different amounts of water in the cups. So therefore, you're not averaging temperature. You're really averaging heat, but you see temperature and heat are not the same thing. So your glasses had different amounts of water at close to the same temperatures, but the amounts of water, even though the temperatures were the same, that made for a very big difference in the mixtures. Are yours closer now?
We got 33 and 16.
Second?
33 and 16.
Okay, and then do your mix.
So the outside,
You can-
just say the amount of water was different.
The amount of the water was different, right? Okay. Now, while y'all are waiting, I may have to, because I used more water than I intended to.
Good job, Sippy.
What you smell like?
Hey, what was the answer to that?
You. Amount of water was different. The amount of water was different, so it changed the temperature.
Use any empty cup you want, but I'll provide the water.
But you got salt water?
Huh?
You got seawater or something?
Yeah, I've got, no, not seawater. Okay.
What about
do you
Dr.
got
Pepper?
here? You already started? Don't. Okay. Yeah, you can zero the scale, but where did you get the water? Huh? Yeah, but where did you get it? Some of the water from down there? We're not using that water. Okay, yeah. So go back to that. Let me see. I need to go get one. Well, I'll let y'all get started. Okay. I brought over some cups. Put the cup on the scale and zero the scale. One of those cups. Or any cup. Any empty cup you happen to have. Right? There you go. Okay, you got it. Zero the scale. Any empty cup. Okay. Don't use this water. And other things. Yeah.
Just the whole cup.
Okay, while y'all are doing that, you can read the directions. Now, wait. Everybody over there is with one team, unless two of you want to come over here, because it's so unevenly divided. Two of you want to come over here and join this group. We'll just do two teams here. Okay? One team over there with that one, and the other two people come over and join these. I'm going to run down. I'll be right back.
You need y'all be quiet while I'm trying to learn.
They have six.
Need y'all be quiet while I'm trying to learn. Trying to learn.
Go to YouTube, put in Dr. Fowler video, and go to 2 hours and 10 seconds.
I want to see that.
That was a new high score on that.
Cam.
You suck.
Can't say Jim voice, they don't know who.
No, we're not doing that.
You suck.
This isn't ball in the cup, people.
Oh, you called that. I can get to there.
They don't count. It's gotta go in.
They said you suck. The pen wasn't even flipping. You been doing it for you suck.
Look, no, that's not the impression part. This is. This isn't hard. God. What's that? What's that? The fuck I want to follow it. Movie this.
He's confused.
I know, I had to go get it. And I sort of may have messed up a little bit. Does anyone have a telephone with a thermometer on it?
Should I make those?
Okay. Now,
I got a vote meter, but it's in the car.
What is that?
okay. Now, you got your hot water there, and you got the measurements on it, right? Okay, temperature and everything.
We all gonna use this one thing for ice or what?
Yeah, I'm just going to give it to you. Okay. Another cup. Zero the scale before you do it, and that one's off too. So zero the scale, and then put some ice in it. And I think I said on here about. Okay. I know we don't have to use this. Make it go faster. How much water did you have? Master water. 350. 360. Put about 30 or more grams of ice in there.
30 grams.
I had 360, that means. Of this?
You get about 30 grams. No, she's still pouring back. Oh, I do forget. Huh? That's hard to have more than 30, at least 30. I'm sure I won't have to mix my Okay. Okay. Measure that. Okay.
It's like 131.
What have you gotten? Well, how much? Okay. Whatever.
Temperature.
Okay. And you already got the temperature. Did you?
42 degrees.
Okay. All right. After that, and another empty cup. Zero it. Yeah. And then put something. How many grams of water did you have?
335.
Huh?
335.
335. You put more than 30 grams of ice in there. Not a whole lot more, but just something more than 30 grams of ice.
More than 30 grams.
Yeah. More than your cup. You zero the cup. You get past 35. Okay, now, what you're to do is pour the ice into the water. Right? Pour ice into the water. Okay? Okay? And you just put that on over the top. Okay. And you'll come back to that in a minute. Okay? You got more than 30 grams of ice? Yeah. Okay, record that. Okay. Now, you got that recorded? Pour that ice into this water. That's your water, right? Okay, pour it into it and use that to cover it. Okay. Now, while y'all are waiting for that ice to melt, what I want you to do is come over here, and I'm just going to estimate room temperature here. I'm going to estimate it to be about 70.
20 degrees Celsius.
Up there? Colder up there? So, what was it?
20 degrees Celsius.
71 up there? Okay, let's just say it's 71 in here, whatever it is. These pieces of stuff have been sitting here in the room, they were in that room, but it's all the same temperature for a long time. So what would you, oh, by the way, we're jumping to the bottom of page 2. Conduction. Here's metal objects and plastic objects. Okay? They've been exposed to room temperature for a long time. You you estimate the temperature of each of those? Metal and plastic. Let's say 71 degrees Fahrenheit. Yes, of course. They've been in the room. They're at the same temperature. It's 71 degrees Fahrenheit. Okay? That's A. Estimated temperature of the metal and of the plastic. I want 71 degrees. We'll just estimate that. Okay? Now, what I want you to do, each one of you can put them down when you're through with them. Take one piece of metal, one piece of plastic, and hold one to each facial sheet. Okay? And estimate which one feels warmer. Do it. Okay, everybody, make sure.
I take his word for it. He got a lot of skin.
Okay? Don't take anyone's word for it. Make sure they're telling you the truth. What's that? Oh, I see. And you're assuming that, right? All right. Does everybody agree that the plastic feels warmer? Why? Why? Say again? Okay, what do you mean by that? And this is the part we skipped today. I'm sorry. We really should have done this. Huh? The conduction of the which? Metal is higher than the conduction of the plastic. So actually what you're doing when you hold them up there, because the plastic is a really lousy conductor, metal is a really great conductor.
You really don't act wild here.
I know, I'm explaining. Okay, taking advantage of the opportunity. Okay, what you're feeling with the plastic is really something pretty close to your skin temperature, because it's not a good conductor, it comes rapidly to pretty close to your temperature. The metal, though, is pulling the heat away from your skin, conducting it down, so therefore you're feeling 71 degrees. So this is feeling around 90, and this is feeling around 71, 75, something like that. So that's why they feel different, though they're at the same temperature. This comes to your face temperature because it's a lousy conductor. This pulls the heat away from your face because it's a good conductor. So which is higher conductivity? Okay. Now go back to your water mixtures and see if all the ice is melted. If it has, measure the temperature of the new water. Sorry, you may not have picked all that up on the. Did all the ice melt? Did all the ice melt? Be sure the ice melted before you do anything. Okay? Okay. There we go. All right, let's get this erased. If I can find an eraser. Here we go. Okay. Y'all can tell me the equation. Okay. What we have going on here now, I think I'll set this up here. It'll be easy to work from. All right. Hopefully everybody has everything filled out up to number E, right?
Yes, sir.
Both teams finished taking your measurements. Yay or nay? Okay. Now, you explain to me what went on in your experiment. Okay? You started off with some, on page 2 at the bottom of the page, you put some water into the cup, measured its mass, and measured its temperature, right?
Right.
Okay. Then you measured ice, mass of ice. Now here's something we're going to assume here. It may not be a great assumption, but I think it's pretty close. Going to assume the ice started at 0 degrees Celsius. Okay? Now the reason that may not have been a good assumption is I had stored it in a freezer and I didn't take it out in time. The freezer was probably somewhat below 0 degrees Celsius, but I tried to hold it warm up with it, while we were coming. And then when I chipped around at it, I hoped it was coming up to 0 degrees. That's all we could do. We couldn't take it. Okay. So then we poured the ice into the water. And then you got a new temperature. Was that different from your temperature on page 1? Okay. So you tell me what happened to the initial water you had. You had its mass, you had its temperature. What did it do? The temperature went down, right? So that was a heat loss, right? Now, what is the equation for heat loss of that original water? Hint, it had a change of temperature. What's our symbol for heat? Q is, whoa, let me get my pen. Okay. Q is equal to MC delta T. That's the that's the heat equation you use on number E. Okay? Now, what mass are you using there? Of the original water, the mass from page 1, 2A, whatever that was. And you, different teams, so don't put down the other team's number, okay? So that's your mass. What was C? Okay, is this ice? This is water, okay? One. The important thing is what? The units. What are the units?
1 gram. 1
Calorie per gram. Degrees Celsius. Okay? So that's your C. You all have your mass. And that was measured in what units? Grams. Okay, whatever your unit was. And then your delta T is what? The difference between page 1 temperature and your page 2D temperature. You have to figure that out. I can't tell you what it is. And your thermometers were in degrees Celsius. Okay? So this is your heat loss. Yeah, at the bottom of the page, the 2B temperature minus the 2D temperature. Not those at the top of the page. The ones at the bottom of page 1 and the top of page 2. Right? That was the water you were dealing with, right? Even though you tried to use different water, but I caught you. Okay? Then you enter that in your equation and see what heat. That's the water that you're dealing with, wasn't it? Okay. Say again? Okay, you're doing kilocalories. Whichever you want to do, I don't care which one you use. Okay, yeah, but, okay, oh, y'all are on the same team. Okay, okay. I don't know. I don't have your numbers. Y'all have your numbers. Well, look at this. Your grams cancel out, and degrees Celsius cancel out. All you're left with is calories.
So it's 4,690 calories.
That's how much heat loss you had.
Just
Do you want it in kilocalories or calories?
Yeah, it doesn't matter to me. You just put your units with the numbers, so it makes sense.
I mean, we put 4,690.
It's up to you. Put your units with the numbers so it makes sense. Okay. Now, I don't know if y'all can see this better. If you're doing, yeah, these are small sheets.
4,690.
Okay. Now,
What's the equation for the heat gain?
for F, that's where we're going next. Okay? Write an equation to determine the heat gain. Now you tell me what happened. After you measured the mass of the ice, you put it into the water that you had, right? And what happened to that ice? It melted. Okay? So what you want to do is the equation to determine the heat gain from the melting ice. Not when it's changing temperature, it's just as the ice melted. So again, you have a Q, and this is a heat gain from melting. And what would that be? MLF, latent heat of fusion. And it's the mass of the ice now, right? Now, I don't know what your mass of ice was. You'll put that down. What's it measured in? Grams. Okay, and does anyone remember what the latent heat of fusion for water is? The mass of the ice, yeah, top of page on number C. Latent heat of fusion.
It was 9 something.
Nope, much bigger. Say again? Latent heat of melting for water. Ice. Okay, well, you got your books? Okay. Okay. Anyone remember what the latent heat of fusion for ice water is? Water, ice. Okay. I'll give you the page number, in fact, if that would be helpful. Calories is what we've been using.
533.
No. 80. You got it. I think you're using latent heat of. Okay. That's 80.0. What units? Calories per gram. You got it. So that's going to give you again calories. You'll have to take your mass of the ice, multiply it by 80. That's latent. That's the heat gain from melting ice. Gain from melting.
Looks like grams meters.
Okay. If there had been a number in front of it, that might would have made more sense. What's that? No, fusion. Latent heat of fusion. Because there's also a latent heat of vaporization, which is much greater. Okay? Now, all that did was to melt the ice. That the heat gained as the ice melted. But once the ice melted, what did it do then? When it melted, it was still at 0 degrees, and it went up to your final temperature, which you had in D, right? So you have another heat gain, and that Q, gain due to, I'll put heating, okay? And what formula would you use for that? Okay, good. I got it. That was helpful. Same as the top. MC delta T. So it's the same thing you use at the top? Nope. I mean, same formula. But What mass are you using now? Mass of the ice. You're absolutely right. Okay? And then what C are you using? No, it isn't. You melted the ice. So it's water. So it's the same as water. 1.00 calories per gram degrees Celsius. And what's your delta T now? How did you get it? Huh? Okay.
That's our gram.
Grams.
So grams and then multiply it by 1.
Right.
Is 35.
Okay, yeah, but then what? You multiply it by your delta T. What's your delta T? That's what I was getting at.
I was waiting on you. I got half of you get half. I you got one.
Okay, what delta T do you use there? Where did you get the 14?
10. Use 10 because it's -10 or
That was the problem we did in the book. Okay. Okay. The ice, when you melted it, it was at 0 degrees, and then what did it wind up with? Whatever you got on D. It warmed up to that. Well, whatever your number was, okay? It's not the same as the delta T up here, because that was cooling delta T. This is a warming. Okay? Now you had one heat loss. Hopefully that's your biggest number, is it? Number E. You had 2 heat gains. Oh, my voice is cracking. I must be reaching. No. So you add those two together, and what do you get?
37, 80.
Whatever you get. Okay? You add the 2 heat gains together, F and G heat gains.
Yeah, 37, 80.
Okay? Now, what's the difference between your heat loss and your heat gain?
One's warm and one's cold.
Yeah, but what's the difference, the actual difference between those? Huh? 910 calories? Is that what you got? Everybody got something pretty close to that? Okay, there's 2 teams, so I wouldn't expect the same numbers. But okay, which of those were larger, the heat loss or the heat gain? The heat loss was larger, huh? Okay, now the question is why? So you write your difference down in the first blank, the second blank, which is larger, and I think everybody said heat loss. Now the question is why? Now this will be a different answer for the 2 teams, I'm guessing. But let me ask you, what was your final temperature of your iced water? 28 degrees? And you were what? 38 degrees. Okay, one team was 28 degrees and one 38 degrees. And what's approximately room temperature? No, that's Fahrenheit. Around 20. Guess what? Your room was at a cooler temperature than the final, and y'all had the cover off of that probably way too long, and especially when you're measuring your temperature, you had to have the cover off, so it was probably losing some of that heat to the room, to the surroundings.
Let the cold out work.
Not quite, okay?
That's our answer.
Yeah, you probably lost heat to the room. Second, that's the why. Now, give me approximately what your difference was. You had 2 teams. Tell me what your difference was. 901 or something like that, you said? 910. I can't write. 910. And what was your heat loss? Right. 46. 909 or 90? 90. Okay, if you got a calculator, divide that. 910 divided by 4690. 0.194. So you had a 19% error, you might say, which isn't bad. With this kind of conditions, it's not bad. The other team, what was your difference? Say again? 900? And what was your heat loss?
14.
I got minus 1400 calories.
14.
Wait.
14.
That was a lot different from having beer and 16 to only have 40 degrees difference. So we didn't have this cheap.
Okay. All right. It's rather bizarre. You had a lot more heat gain here than you had heat loss there, right? Is that what you're telling me? Okay. Number 41. Huh. I wish I'd have been watching that a little more closely. Sure that was a 38 and not a 28?
12 total.
Okay. That's rather remarkable. You wouldn't have had more than that. But anyway, so your answers are going to be different at the bottom because you had greater heat gain than you had heat loss. So anyway, you generally get, okay. I can't account for that.
We got one more question now.
Okay, what's that? What'd you say?
The very first question, score
The very first question.
at the top of the page.
Mass of ice or? Oh, score? Oh, I see. I can't hear you. Okay. Probably around 12 or 13. Nah, I'm just kidding. Okay.
Out of 14, I might as well go and drop by the mouth.
Okay. All right. You ought to be pretty close to 25. I mean, we did it all together. So if you
I'll let you score that one.
thank you. Because if you get it wrong, you lose another point. Okay. So okay. All right.
Did it save the ones I got?
Now, this one didn't have one of the questions because this was one I made up. Did you feel like this lab was worth it?
Yes.
Okay, makes sense. Okay.
Is that for brownie points?
No, that's all wipe it. Okay. In some sense, maybe a little brownie, but never mind. Okay. All right. Any questions on the lab? Okay, y'all want to stay down here to do the test or go back up to the room? Do it here? Okay. All right, let me go on and shut down. If there's no more questions, I'll shut off whatever this is called, Screencast-O-Matic.